From ContainerDays Hamburg, this video is proudly presented by Dux IT.
Today we are going to talk about the art of garbage collection in Go. And I want to start with this quote from Go FAQ. How do I know whether a variable is allocated on the heap or the stack? And I love the answer. You don't really need to know this one. That's the answer from the Go team. But the reason I'm here today is because memory is a finite resource, and as programmers, we should use this wisely, whether choosing the right data structure or thinking about more aggressive garbage collection algorithm, if it's possible. And I have to admit that Go garbage collector is great, but it's not a silver bullet. It still has some issues here and there, and memory leaks are still possible with this. And if I recall this correctly, today is going to be another talk about exactly this problem. And before we move forward, I want to ask everyone, does anyone know what was the first programming language that implements garbage collector and when it was created? If you know the answer, please raise your hand. If you don't know yet, at the end of this talk, I will give you the answer. So let's first start with the stack. As title says, stack is fast, clean, and organized. Stack implements LIFO queue, last in, first out. You can think about this structure, this way of organizing memory as a stack of plates, where the one that you put on top will go away first. Exactly the same will happen with stack, so we can keep adding some elements to the stack, and when it comes to remove elements from the stack, we will start on the opposite direction. Right. In Go, stack is pure Go routine. So every single Go routine in Go will get its own stack. Within a stack, as I said before, this example with a stack of plates, instead of plates, we operate with a stack frame. Stack frame is the amount of memory that a function needs to execute, and actually every single stack frame that you can see here attached to a specific function. And at the bottom we have a stack pointer. So a stack pointer actually helps Go runtime to allocate memory really fast, because we know exactly where we need to start allocation. The stack frame size is known at a compile time. So basically we know where to start, we know how much memory do we need to execute this or that function. And objects in stack, they have really short lifetime. So basically their lifetime ties to a function. Once we exit from the function, stack pointer moves up, and everything below stack pointer becomes invalid memory. So basically that's the way we can free up memory in a stack. Let's take a look at the stack in action. This is very simple, very artificial piece of code where we have a main function that consists of two variables. It then calls another function double that does the very simple thing, is just double the number that you pass to it. And let's take a look at how stack looks like for these two functions. So initially, Go runtime will execute the main function. It will create a stack frame that has enough room for two variables, A and B. Then the execution will be handed over to the double function, and at this point a stack frame again must have enough room to hold all the inputs, outputs, and local variables. So in this specific example we don't have any local variables, however we have inputs and outputs. And once this double function is done, it will the stack pointer will move up, and the previously allocated stack frame will disappear, and we are back to our original stack frame. Another example of a very similar function, but now instead of passing a variable to the double function, we pass an address of the variable from a upper stack frame. So this is how it looks like in action. So we actually are going to modify, in the double function, we're actually going to modify a variable within a main stack frame, and this one also works. So with this one, I want to highlight that when it comes to pointer, it's also possible that everything stays within a stack. So no heap involved here so far. Another example here would be, what if function wants to return a pointer? Let's assume that for now we have no idea about heap and we only know the stack concept. So initially it's going to look exactly the same as the previous one. In our stack frame we are going to keep a pointer. Then we call a start point function. We allocate another frame, stack frame, keep a variable p there. And once we exit from a start point function, this is where we will fail, because now we assume to point to something that below the stack pointer, and below the stack pointer memory is invalid, so it's not possible. This is where I want to introduce heap. Heap is a shared, flexible, and a little bit of messy. Shared means that it is available from all the Go routines, from all the stack frames, from everywhere within your program. Objects in heap, they have a longer lifetime. If you take a look at this square with a lot of question marks, basically no one is pointing to this object, and it still lives there in a heap, and it will remain there unless until garbage collector will come and say, hey, you have to free up the space. Another thing about heap is a slower allocation compared to stack. Why? Because things are a little bit messy there in heap, and let's say for this new object we have potentially three spots to store it. So memory allocation algorithm should decide which one of those should be occupied, and yeah, this is not like a super easy. If you remember with stack, we have just a stack pointer and we just go from there. Another problem with a heap is fragmentation. So technically speaking, in this heap we have 3 bytes, those gray squares there. We have 3 bytes available. We have object with exactly the same size, 3 bytes. However, we cannot store it in this heap because for the object we need 3 bytes, continuous 3 bytes, whereas there in heap we have those 3 bytes. They're very fragmented in a different places. So unfortunately we cannot use this. So we need either more memory or wait until one of those spots will be available. So then we can fit our object there. So let's take a look again at our previous example. Now when we know about heap, the way it's going to work. At a start point function, instead of creating a variable p in stack, it's going to be created in heap, and in a start point frame stack, we're going to keep an address referring to this to the heap, and once we exit from start point function, in our main function will start pointing to the heap. This is how this problem is getting addressed with the heap. So stack and heap, they work great together. How does Go know whether a variable should stay in heap or should escape to, or should stay in stack or should escape to heap? This is what they call escape analysis. Escape analysis is a compiler optimization. So basically what compiler does at a compiling time, it will go through all of your codes and will decide whether or not a variable should stay in stack or escape to the heap. So the Go team constantly improves memory management in Go, and things might be changing from one version to another, but there are 3 rules that most probably will remain in place for a long time. The first one, if a variable size is dynamic, then there is a high possibility that this variable will go to heap. This is like, again, another artificial example where I'm creating a slice and the size of this slice is passed by a variable. So at a compile time, we don't really know what's going to be the size of this one. So it's better to move it to the heap. This is a good example of how you can see escape analysis in action. So you can basically use a GC flag -m. -m is for printing out all the optimizations that Go does. And you will see exactly this line that making a new slice will escape to heap just because it has a dynamic size. A second thing is if a variable is too large for the stack. Here you can see a few examples, again with the slices, because it's just easier. And the very first one is going to have like a size of 8 kilobytes on my 64-bit machine, and the next one is just one element bigger, and that one will escape to heap because this one crossed the limit of the object size for the stack. Another example with Boolean variables, with the Boolean type. Basically, the third slice is going to have exactly the same size as the first one, 8 kilobytes, and again, if you cross this limit by one element, it will go ahead and escape to heap. And the last one, this example that we're familiar with, is when a variable outlives its function. So basically, when we exit from the function and we know that we want to use the variables that were produced within this function, those variables, they will escape to heap. So a quick summary, heap versus stack. It's a fast versus slow memory allocation, strict versus flexible data organization, short versus long lifetime, and self-cleaning versus garbage collection. And I want to highlight this part, fast versus slow memory allocation. This is, again, this example that we saw before when we just create a variable and an integer variable, and then we return it. In the first case, we return an integer itself. In the second example, we return a pointer. And this is the benchmark for those two simple functions. As you can see, when we stay within a stack, it requires just 0.94 nanoseconds per operation. There is 0 allocations, and it's super fast. When it comes to heap allocation, you can see that it's roughly 10 times slower, 9 times slower. It's 8.3 nanoseconds, and we can see that there are some allocations happening. And again, this is like completely artificial example. Most probably no one is going to do anything like this. And with this one, I just wanted to show you, want to demonstrate you that it's really about memory allocation, because within this function you can have some for loops or some other business logic that will even more slow down your code execution. Go memory allocation is a very interesting and a very complex topic, and I want to just give you a brief overview of this one. So Go memory allocation model based on a tcmalloc product, which is developed by Google to improve memory allocation in languages like C and C++. It represents memory in a hierarchical way. You can see this in this picture, like a high-level overview of all of those levels that are there in the memory. And it aims to reduce fragmentation and the amount of system calls that your program will do in case it needs more memory. Over the next few slides, I'm going to go through this picture step by step so you would better understand what's happening there. Before we jump into this one, I want to point that in Go, when it comes to object size, there are two types: big object, everything that is bigger than 32 kilobytes, and small object, everything that is less or equal 32 kilobytes. What Go does, it classifies those small objects further into 67 different classes, and that one will help reduce the fragmentation and minimize memory waste. So it's not like a full table. I just brought here like a few classes. So for example, class 1 suitable for all objects from 1 to 8 bytes, class 2 for all objects from 9 to 16 bytes, etc. For every class, Go will give a span of a specific size, so like class 1, 8 kilobytes, and number of objects that will fit into this span is basically just divide the span size to the object size, and that's how you will get 1024. The last column is very interesting, max waste. What does it mean? So basically, in a class 1, the maximum object size could be 8 bytes, but the smallest one could be 1 byte. It means like, if you're going to store there just 1 byte, the remaining 7 bytes are going to be just wasted. And this is where you get this number, 87%. This, unfortunately, is something that's possible to avoid in some cases, but not all the time. And this column, tail waste, is also an interesting one. So if you take a look at the class number 5, it stores object of up to 48 bytes, and within this span, it can only fit 170 objects. So if you multiply 48 by 170, you'll get a number 8160. So remaining 32 bytes, unfortunately, are going to be wasted anyway, and there is no way to avoid this one. Now we are going back to this picture that you saw before. So in Go, I don't know if you're familiar or not with this one, G stands for Go routine and P stands for the logical processor. Most of the time, I would assume that the logical processor, the amount of logical processors that are available for you is the amount of cores that you have in your machine, but that's not always the case, and you can change this one. So let's not go into details of Go scheduler, but the idea is like every Go routine is going to be scheduled on one single logical processor, and all the execution will happen there. Why do we need this one? One of the reasons is there is an M cache that is going to be attached directly to one of those logical processors. Like basically, every logical processor will get an M cache. M cache is suitable for objects less or equal 32 kilobytes, so those that are classified from 1 to 67. And M cache operates with M spans, so you saw those spans in the previous table. And those M spans, they are organized into those M centrals, which is centralized space to store all the M spans of a specific class. So basically, every M span is going to be attached to M cache. M cache is lock-free because it works only with one logical processor, whereas M central, if you want to request something from M central, that's where you will hit a lock mechanism. So basically, just because there are multiple logical processors accessing this one. So for example, if your M cache fully utilized an M span and it needs more, it needs to store more objects of this specific class, what M cache will do, it will go ahead and request additional M span from the M central. In this case, class 1 has additional available M span that's not occupied anywhere, so M central will give it to one of the M cache on request. In the case of class 4, we see that it's fully busy, so it needs M central needs to request another M span. For that one, it will go ahead and talk to M heap layer of abstraction, which is also implements locking mechanism when it comes to accessing M heap. And M heap is the one that talks to the operating system when it comes to requesting memory. So the way M heap works, it will go ahead and request a big piece of memory from the operating system, and it will call it arena. It will further slices this arena into a multiple pages, 8 kilobyte each, and what M central is going to request, it's going to request this raw memory page from the arena, from M heap and arena, and then it will operate and will be able to allocate it to one of the M caches. And what about objects that are bigger than 32 kilobytes? Oh yeah, sorry, one more important note here is this piece of memory arena that Go requests from the operating system. This is a virtual memory, so it's not a residential memory. That's why sometimes when you look at top output or PS output, you might notice that Go application consumes a lot of virtual memory, but not really that much residential memory, and that's the way it works. So this helps to reduce number of system calls. When it comes to objects that are bigger than 32 kilobytes, it's very easy. There is a so basically, Go runtime is going to skip all of those levels like M cache and M central, and is going to request pages directly from M heap. Well, as you can imagine, this is also a slow process because here we have all classes available and it's all cached. Now, when it comes to a garbage collector in Go is concurrent, tricolor, mark, and sweep. Concurrent means that it executes alongside with all other Go routines. Mark and sweep consists of two parts, as you can imagine. One is mark, second is sweep. So, and when it comes to mark phase, it actually uses those three colors. White for it's an initial color, and the color that is going to be used for objects that would be collected. The gray one is marked but not yet scanned for pointers, and the black one is marked and scanned, so confirmed safe. So that's a live object. Next, and the sweep part is basically works mostly with white and black objects. So mostly with white objects is basically go ahead and remove all white objects from the heap. So the way it works, again, the mark phase goes first. This is how your memory will look like if you take a look at this through the ghost eyes. You have a heap, all the objects there, they have a white color, that's the initial color for all the objects in heap. Then garbage collector will scan all the global and stack variables to see whether or not they're pointing to a heap. And if that's the case, and just before that, it will first enable a write barrier. A write barrier is a technique that allows Go to execute concurrently with all other routines. And the idea behind write barrier is to notify Go runtime, like, well, I'm working on the marking phase right now. If you're going to create any new connections from stack memory to a heap memory, just let me know, so I will ensure that this new connection will be marked appropriately. And then it will start tracing objects from stack to heap. Those global and stack variables, they're kind of a root of this graph. The first object in a heap will get a gray color, and this is where it's marked but not yet scanned for pointers, because if it has pointers, or you can call them childs, it will first go ahead and recursively go through all the childs of these objects. Those childs are scanned and marked as black because they don't have any other pointers. All the parent edges of this graph will also get a black color. So this is how it will look like at the end of the mark phase. What will happen next? Go will mark all the objects, and then it will temporarily stop the world, not the world, but the Go runtime. So basically, all Go routines that are executing at the moment, they will stop completely. Go will remove a write barrier, will complete the mark phase, and after that, this is how your heap will look like. So it will only consist of white and black objects. And then it will hand it, the mark will hand it over to the sweep part, and the sweep part does a very, not very, does a very important job. It's actually go through the objects in heap and will free up those that are white, that are not available from the stack or global variables. Okay, so let's quickly take a look at Go garbage collector in action. So heap size dynamically adjusts at a runtime. What does it mean? So when you start your program, you need to understand where, like not you, Go runtime needs to understand when it has to trigger a garbage collector. And initially, the initial heap size or initial heap goal would be roughly like 4 megabytes. It really depends on some settings and on a platform, but let's say 4 megabytes. And once your heap grow all the way up to 4 megabytes, then that's the point where garbage collector will be triggered. So what will happen next after garbage collector will scan all the objects? Let's say in this example, it will say like, okay, all 4 megabytes are live heap memory, they are in use, we cannot remove anything, that's fine, that's okay, we can continue. But then we need to raise this bar for the heap goal. For now, I would say that Go is going to double the number of that represents the live heap memory, and that's going to be a new bar, like in this example, 8 megabytes. So next time, garbage collector will be triggered once your heap grow all the way up to 4 megabytes. Next time, after next cycle of a garbage collector, let's say we have 3 megabytes of a live heap memory, that's where we can technically lower the bar, and again, it would be the double size of a live memory. In this case, it's 6 megabytes, and another example is like, you can see that it's keep doubling, and this kind of helps to adjust heap size and when we should execute when we should trigger a garbage collection cycle. So This is all great, this all works well, but there might be a few questions. So first one, what if I want garbage collector to get executed a little bit earlier? Or what if I want to give it a more room and like execute less frequently? That's a great option because the garbage collector is not free. You have to pay with your computer resources with some additional memory. And this is how you can tune a little bit of garbage collector. So this formula actually tells you how Go calculates the heap goal. It's basically live heap plus GoGC variable divided by 100 and multiplied by the same live heap size. So by default, GoGC is equal to 100. So that's how it doubles. That's what you can change through an environment variable, or if you prefer, you can do this from the runtime. You have to use the debug package, set GC%. Let's say if you set 1,000 instead of 100, then the initial heap goal would be not 4 megabytes, but 40 megabytes. And let's say for the second part, the heap goal would not be additional 4 megabytes, but again 40 megabytes because it's going to be 10 times bigger. And it works the opposite direction, so we can lower this number. That one will mean that you will get less memory and more frequent garbage collection execution. You can also completely turn off a garbage collector by setting this to off. Another thing that heap can grow all the way up to sky, and there is no limit for the heap. And starting from version 1.19, the Go team implemented this another runtime and environment variable Go mem limit that sets a soft limit for the Go, when the soft limit will kind of help to understand like that's the amount of memory that's available, so please trigger a garbage collection cycle more frequently. And again, this is a soft limit. Technically, it can go over this limit. There is nothing wrong, but you need to understand that this is a soft one. This is a quick example how you can potentially debug Go garbage collector. So you have to use this environment variable Go debug, and you have to set GC trace equal to 1. It will give you a huge output. So this is just like I cut half of this, and what is important here is you can see exactly where garbage collector is going to be triggered, how much CPU is going to it's consumed, and what was the time stamp of the program execution. And the most interesting part here would be those three numbers with arrows. There basically represents a heap size at the garbage collector start, at the garbage collector end, and the live heap. And the next one, you can see that's what's going to be a next goal for the heap memory. This might be very interesting information if you want to really dig deep into details. But again, please pay attention that this is all debug, and this is also debug package. So you have to be very careful. You really need to understand what you're doing and how that might affect your potential production environment. So, quick summary. You definitely should trust the Go team because they know what they do. They run a lot of Go code in production, so they really work on a lot of optimization. You should definitely avoid premature optimization because memory management might not be the one that is causing your issues. Maybe you're using like a nested for loops, or you're waiting for long from some disks or network. And this is not the end, because if you really want to understand what's the problem with your program, you need to profile your program to better understand where the bottleneck is. And do you remember this question from the very beginning, like who was the first? And the answer might surprise you, because I was actually surprised. And that was Lisp in 1958. So this topic is really old in the industry. So a few references here. Definitely go and read Go FAQ, Go Guide to the Garbage Collector, runtime package including debug and preprofile. A few linters here that can help you to write better structures. They will kind of point you that this structure is not optimal from the memory point of view. And two books that I would highly recommend. The first one, 100 Go mistakes and how to avoid them. I personally think that this is a book that every Go programmer must read. And if you really want to go into details of any garbage collection, you need to read this book, the Garbage Collection Handbook. This is amazing, amazing one. And I want to give a special thanks to my friend, colleague, amazing engineer and technical reviewer of this talk, Sarah French. Thank you. I am happy to answer your questions.
Is there any scenario where I would want to turn off the garbage collector?
Yeah, so for example, you have a program that you want to really execute fast and you don't really care about the amount of memory it's going to consume. It can be like, let's say, a small, let's say it's script that will execute 10 seconds, and even within 10 seconds, garbage collector will be called multiple times. So if you really want to avoid and win some CPU cycles, that's where it will work. But again, it really depends on your needs. Sometimes you really need this one.
Thank you. Stack object size. You stated the object will escape to the heap if its size exceeds 8 kip. But both examples were slices of 64 each.
So not really. I didn't say that it will exceed 8 kilobytes. It really depends on an object. In those examples, yes, they exceed 8 kilobytes. And I'm not quite sure why it refers to 64 kilobytes each, because those slices there, oh yes, my mistake, sorry, you're right, the one who sent this question, you're right, because an integer is 8 bytes, and yes, sorry, that was my mistake, that's the right one, yes.
No worries, that's all good. Does the Go garbage collector also defragment heap memory?
No. No, basically, as you saw on this like a giant slide with a lot of layers, that's the way it avoids fragmentation. So once objects are freed up or whatever, Go doesn't move those objects within memory, so they all stay in their places.
Wonderful. Thank you so much.
Thank
that
you.
was an incredible talk. You answered all the questions. So I would say, oh, there's one coming up again. Okay, we still have time for that one. What got you looking into Go memory internals? Was it for fun, knowledge, or were you investigating or fixing something specific?
I was investigating one issue that I had in one of my projects that was a Kubernetes operator. So I noticed that some of the functions there, they're executing slow, but not really that much slow. Because at the end, I want only 1% of a CPU cycle. So the idea was that I was passing some objects back and forth, and they were all allocated to heaps. So I ended up with just working with pointers, and yeah, that's the answer. And then that was like more like a lot of fun knowledge, because I really wanted this like how does it work internally, because I just changed, let's say, one line and I got like a good performance improvement. So that was got me curious about this topic.
Wonderful. Thank you.
Thank you.
So I think now we have it. Aleksandr, thank you so much for being with us. I love your mascot, by the way.
Thank you.
I have to make a picture of that afterwards. Thank you so much for being here. It was a great talk. That's your round of applause.
Thank you for having me.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.